Hello, in this video we are going to talk about dimension analysis and its uses when it comes to turbomachinery. So first, you may be wondering, what is dimensional analysis? It is a method to comprehend and check relations between physical variables in a system by means of working with their dimensions. But what does dimension mean? Dimensions are the identity of a physical variable. You can tell what a number means physically by looking to its dimensions. There are a handful of basic dimensions. Mass, length, time, and temperature are the ones that we will be using. The dimensions of any other physical variable are combinations of the basic ones. Speed, density, and force are some examples. And what do we use dimension analysis for? It is commonly used to check whether an equation is correct or not, but also it can make us able to determine relations between variables by running a small amount of experiments with a lab-scale prototype. So first, let's get started with the Buckingham P theorem. This is a very important statement that allows us to obtain a set of non-dimensional parameters that will help us understand the system we are studying, and, through experimental data, will give us a correlation between them. The Buckingham P theorem states that we can transform a relationship between n parameters of the form that follows into a corresponding relationship between n minus m independent dimensionless parameters in the next form. Usually, m is equal to r, where r is the minimum number of independent dimensions, for example mass, length, or time, required to define the dimensions of all the parameters. We will show the way to use this theorem with an example. Imagine we are to obtain an equation to determine the loss of pressure for an incompressible flow, a liquid, through a straight horizontal pipe. The first step is to list all dimensional variables involved. We must have into account every single variable that we think will influence the system. In this case, we can think that the pressure loss is likely to be influenced by the pipe length L, the average velocity V, the fluid viscosity mu, the pipe diameter d, the fluid viscosity ρ, and the roughness height E. That makes n equal to 7 dimensional variables involved. The next step is to list the dimensions of all parameters in terms of primary dimensions. For example, v is speed, which is measured in meters per second. In terms of primary dimensions, it is length per time, L per t. In this case, the only primary dimensions to use are mass, length, and time. So, we only require 3 basic dimensions. Thus, m is equal to r, which is equal to 3. Third step. In this step, we must select a set of r-dimensional parameters that includes all the primary dimensions. We will call these parameters repeating parameters, and they must be independent. That is, we must be able to obtain the rest of the dimensions using our repeating parameters. For example, we cannot choose L, the length of the pipe, and D, the diameter of the pipe, at the same time, because we wouldn't be able to obtain the rest of dimensions with any set containing them. In this case, R is equal to 3, so we can choose, for example, the density of the fluid, the velocity of the fluid, and the diameter of the pipe. Now, we must set up dimensional equations combining the parameters selected in step 3 with each of the other parameters in turn, and solve them to form dimensionless groups. Each dimensionless group will be composed by the repeating parameters and one of the remaining variables, and, as they are dimensionless, we can set the next equations. For example, to obtain the parameter containing the pressure loss, the parameter will have the next form. And, as it is dimensionless, it must satisfy the next equations. Thus, the dimensionless group is the next one. Congratulations! You just obtained your first dimensional parameter. Now, it's just a matter of obtaining the rest of them. Another non-repeated parameter whose dimensionless parameter must be obtained is the viscosity. Repeating the procedure, we obtain the next parameter. Then, we do the same for the length of the pipe. And finally, we repeat the process for the roughness height. With this, we have obtained all 4 parameters we had to determine. Thus, the relationship is the one that follows. It must be clear that the theorem is not enough to determine the functional relationship between the dimensionless parameters. It must be determined experimentally. In fact, this relationship correlates the experimental data well. To obtain the head loss H sub L in a pipe, the next equation is often used. Where F is the friction factor. In laminar flow, it depends only on this dimensionless parameter. But in turbulent flow, it depends on these 2 dimensionless parameters, confirming what we just obtained. Also, though experimental data are necessary to determine the relationship, the P-theorem can help us providing the best way to do it. Otherwise, we would have to study the influence of every single parameter on the pressure loss, all 6 of them, independently, represent the data, and make sense of it. However, using dimensional analysis, we would only have to study the influence of 3 dimensionless parameters, making the process much simpler. However, we must take into account similarity. Dimensional analysis is a useful tool for predicting the behavior of a full-scale prototype by data obtained from a lab-scale model. This data will be correct if the prototype satisfies similarity, which means that we must make sure that all but 1 dimensionless parameters obtained have the same value in both cases. By doing that, the remaining parameter will have the same value too. In order to guarantee similarity in our previous example, as there were 4 dimensionless parameters, we would have to make sure that 3 of the dimensionless parameters remained constant. There are some dimensionless parameters that you will encounter frequently. Here it is a list of some of the most common ones, including Reynolds number, Euler number, Fruit number, and Mach number. Now we'll talk about specific speed and specific diameter. Dimensionless parameters can also help us select the adequate type of turbomachine for a given duty. These parameters are the specific speed and the specific diameter, where n is rotational speed in Hertz, q is flow rate, measured in meters per second, and h is energy transferred in meters. The specific speed is sometimes expressed in radians just by multiplying by 2p. For compressible flow, the next equation is used. Finally, the coordinate diagram, which is shown next, shows on the right side the recommended turbomachine to be used for a specific speed and a specific diameter given by the conditions the turbomachine must work at. It serves as a first idea of what type of turbomachine is the most suitable one. So, as you can see, dimensional analysis is a great tool to have for an engineer, and I hope you found this video helpful. If you want to know more, look for the other videos of this course of turbomachines. Thanks for your attention.